Hello, sixth graders and everyone else. This is your homework from the day before yesterday, 10:25, and it was a review on information that you already expected to know, but I don't expect you to know it, but I want to make sure that we have a good grasp on understanding what's happening. So these first two problems ask us about writing equivalent fractions using multiplication. And what this is, this box can be confusing, but we're basically scaling up this fraction to an equivalent fraction by multiplying the numerator and the denominator by the same number. That's the exact same number, and it can be any number of your choosing so long as we know that it has to be the same on the numerator and the denominator. So to make this simple, we'll multiply it by 2 over 2, which would give us 10 over 14. And we know that these fractions are now, my bad, that these two fractions are now equivalent fractions. Okay, again, over here, maybe we want to multiply it by 8 over 8. Multiply, 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 multiply. Which would give us 64. I'm testing my multiplication fact knowledge. 64 over 72. Okay, and again, these are equivalent fractions, which means they represent the same quantity. However, this fraction, this whole is cut up into only 9 pieces, whereas this whole is cut up into 64. All right, moving on. Now this is the same process down here, except it's asking us to write each fraction as 2 equivalent fractions using division. The only more difficult or more challenging part in writing an equivalent fraction using division is we have to find a number that is, hopefully we will find a number that is that is a factor of both numbers. Now to get it to simplest form, we want to find its greatest common factor, but in this exercise we don't have to do that. And if we want to keep it simple and divide each one by 2, then we would have 6 over 9, or we could divide each by 3, and that would give us, or 6. Divided by 6 over 6, which would give us 2 over 3, okay, which would also be both numbers' greatest common factor, and it would reduce this into simplest form. Looking at this one, I say start with 5. We're dividing both by 5. I know that both are divisible by 5 because this one has a 5 in the ones digit and this one has a 0 in the ones digit, which indicates that both are divisible by 5. Now 5 goes into 120 times, so this would be 20 plus, and 5 goes into 70 14 times, so that would be 34. 5 goes into 49 times, another 9 times, and 1 time, which would give us, 19. So then we have 19 over 34, and again, these are equivalent, but they are not the same, but they represent the same quantity. However, this represents the same size whole that's cut into 34 pieces, and we have 19 of them. And this is the same size whole, but it's cut up into 170 pieces, and we have 85 of those pieces. I'm so sorry. I had to go back and check my facts because it is the end of the day. And when I'm looking at, oh no, it won't let me erase this because I already wrote it. So we're just going to write over it in a different color. But this is 8 because 5 goes into 48 times, and this is 17. Hopefully, I know that some of you caught that and you were thinking, Miss Petito, you are so wrong. And good for you for catching it and thinking about it as I'm going over it. So on to the next one. So this next set of problem is asking us to write equivalent fractions, but it's a little bit more challenging in the sense that it, let me pick a different color, in the sense that it is only giving us part of, or it's giving us part of the equivalent fraction. Now, I guess we could view it as more challenging or a little bit easier, to each their own. But in this one, what we're looking for is, all right, so we know that 5, 6 is being scaled up to something over 54. And we need to find out, or what I would first ask myself is, what is the relationship between 54 and 6? How do I get from 6 to 54? Now, I know that when I'm writing equivalent fractions, the two operations which allow me to do this is multiplication and division. So if I'm looking at addition and subtraction, I know that those aren't going to work. So knowing that 54 is bigger than 6, I must be multiplying 6 by something. So what am I multiplying 6 by to get to 54? If we know our multiplication facts, great. If we're not, if it's after school and your brain is tired, go ahead and take out a calculator, because again, I want you to be thinking about the concept and not the computation. But to get from 6 to 54, we have to multiply 6 by 9. Now, as we saw in the last slide, getting to equivalent fractions, it has to be by the same exact number. Not an equivalent number, but the same exact number. So if I multiply 6 by 9 to get to 54, I must have to multiply 5 by 9, and that will give me the answer here, which would be 45. Yep, because 5 times 9 is 45, not 5 times 9 is 40, because I'm scaling it up proportionately. Now, looking at number 6, okay, a couple of us did this different ways, and I will show you more ways at the end, but I want to get this out. So we're going to save number 6 and come back to it because we need more room. So save, it'll be at the very end of this presentation. Now, 24 over an unknown quantity is equivalent to 3 over 5. Looking at the relationship between 24 and 3, it's getting smaller, so I must be dividing 24 by a number. What number would I be dividing 24 by to get to 3? Again, those multiplication facts, that would be 8. What number goes into 24 3 times? And that number is 8. So I must have to have a number that when we divide it by 8, it is equivalent to 5. And if we know the inverse operation of dividing by 8 would be multiplying by 8. So to get from 5 to whatever it used to be, we need to multiply 5 by 8, which would give us 40. Okay. Over here, how did I get from 60 to 12? We want to look at the relationship that we find between the numbers. 60 to get to 12, 12 is smaller than 60, so I must be decreasing the size or taking part of it. And I know that 12 goes into 65 times, so I must be dividing it by 5. Again, coming up here, we're going the opposite way, which means we need to use the inverse operation. So we would be multiplying 11 by 5, which would give us 55. Okay, and I love the visual here that we see in the quantity. 5 being our whole, and spare me, I'm going to wax poetic for a second about our models. But if we're starting with 2 fraction bars that represent our quantities here, 11 over 12. So say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh man, yeah, that's 12. Okay. Then we have 1, 2, 3, 8. I promise there will be a point in here. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is where we see it connect to ratios and fractions connect to ratios. So if we have 11 over 12 here, I'll use this color. If we have 11 over 12, okay, or 11 to 12, each unit is worth 1. But if we scale it up to represent 55 over 60, each box would then be worth 5. So this would be 5, 5, 5, 5, 5, and so on and so forth, which would then give us 55 over 60. And I will stop there. writing each fraction in simplest form, I'm assuming that, we're all pretty good there. It should be 4 over 7. Here we have 12 over 64. Well, 12 doesn't go into 64 because it goes into 65 times, so I know that's not the answer, but I know that 6 times 6 is 36, and I think 6 times 8 is 64. Again, I apologize for my late evening. It's not even late, just after work. My brain. The 64 divided by 6 is going to give me, it's not divisible by 6, is it? It's divisible by 4. There we go. So it's going to be 3 over, it's not divisible by 4 either. I am so right. It is divisible by 4, 3 over 16, which can't be reduced anymore because 3 is prime and it does not go into 16 evenly. So this is our answer. This brings us back to converting measurements. I'm going to use this space over here to do the work. I just realized you can't see where I'm pointing my pen. This space over here to do the work. So if we have, a lot of times kids get confused get confused by, do I multiply, do I divide, what's happening? And it's really a simple way, again, to use a model to help them figure out what's going on in the problem, which is going to, again, reinforce that visualization. It's going to give them something to fall back on and to reference often. So this is one area that I really love to have them use visual models. And one student said that her teacher taught her this last year. Of course, it looked much nicer, but this is totally okay, if that's what they refer to and what they know. I would say using our fraction bars is also awesome. So if we have 1 gallon, if this represents 1 gallon, how many quarts are in a gallon? Well, I know there's 4 quarts in a gallon, and that's something that they have to know, or something they can look up. So then if we have 6 quarts, how many gallons would that fill? And that would fill 1 1/2 of a gallon. Again, just having them do the drawing it out to help them figure out what's going on and to help them solve it. If I have 72 inches and I'm dividing it by feet, this one is great. If they're doing it in a number line, you can just put 0, 72. I always tell them that they aren't, they don't have to draw every number on the number line. They can just draw some line and name it. So we name this 72 inches. And when we're dividing it into feet, I know that there's 12 feet in 1 inch. I'm sorry, there's 12 inches in 1 foot. So this would be 1 foot, and it would be 12 inches. My next foot would be here, and I know that it would be 24, so on and so forth. But ultimately, if they see, okay, I'm dividing 72 by 12, to help them see what's happening, then they don't need to complete the visualization or the visual representation. It just needs to help them figure out what's happening. So again, that would be 6 feet. You can erase all of this madness. Not that we necessarily need to. So these ones are always fun. I think they're all really good at them. And I almost don't even want to solve it because I know they love it so much. But this represents, 36 represents this quantity. We don't know this quantity and we don't know this quantity. But if we know that these two are the same size, because they clearly are, 36 must divide evenly between these 6 boxes. So 36 divided by 6 would be 6. And if each box is 6, then this must be 6 each as well, which would be 24, and this would be 12. And I will stop there. Oh, just kidding. Number 6 that I skipped. Now this came up a lot, and some students had solved it using their thinking, and some were like, what? This can't work. There is nothing here. So what I would ask them to do and what I want them to do is to see the relationship between these two quantities. So what is the relationship? We don't know what the relationship from here to here is because that's our missing quantity, but we know that 12 and 20 must be connected. So I am going to show you one way, and then I'm going to show you another way. The first way is, what is the relationship to 12? Well, we know that 20 is 8 more than 12. Okay, and if we know that 20 is 8 more than 12, well, okay, I can't add 8, right? Because if we're writing equivalent fractions, we have to use either multiplication or division because it has to be proportionate. So I can't add that 8 down to that 15, okay? So since I know that it's multiplication, because 20 is bigger than 12, so I must be multiplying something, I need to figure out, okay, well, what am I going to be multiplying 12 by to get 20? So here's where I'm then going to look at what is the relationship between 12 and 8. Well, in class today, a student said, well, 8 is 2 groups of 4, and 12 is 3 groups of 4. Okay. And I didn't have this nifty app, so I was using my fingers and I overlaid them. But when we draw it out like this and look at the relationship quantitatively, it was quick for students to see that, oh, 8 is 2/3 of 12. So then we ask, all right, so what if we multiply 12 by 2/3? That would give us only 8. But we have 1 whole 12 plus our 8, or 2/3. So we're not just multiplying it by 2/3, we have to multiply this by 1 and 2/3. And if we multiply 15 by 1 and 2/3, that would be 15, and then 2/3 of 15 is 10, plus 10 would be 20 over 25. And our missing link is 25. Now, a student demonstrated their thinking in this problem was they said, well, 12 over 15. What's the relationship between 12 over 15 to 20 over some number? Well, I know that I can write equivalent fractions using either division or multiplication. So what if I scale this down and divide it into its simplest form, or divide it by 3, which would give me 4 over 5, which would put it in its simplest form. So since 4 over 5 is equivalent to 12 over 15, 4 over 5 must also be equivalent to 20 over whatever this number is, because I divided both the numerator and the denominator by the same number. Sorry, I should have changed color. Therefore, I can look at it as, what is my relationship of 4 to 20? Well, to get from 4 to 20, I have to multiply it by 5. Therefore, I must have to multiply 5 by 5 to also find the denominator here. That way is much less confusing. Both ways work. There were also other students who came up with other ways to solve this problem. So again, it's all about thinking, the connections, the making sense of what's happening. What do I know? What do I know to be true? What is the authority here? And the authority is always math. So we always want to push students and press them, okay, what do I know about this? What do I know to be true? What are the hard and fast rules of math that are always provable and always true? And can I extend that information to this new problem?